What I'm going to do is describe the panel. Now, the live builds have been part of the Modern Hydronics Summit for a number of years, and traditionally these panels have been built around boilers, typically with some zoning. In some cases, it's been combi boilers, so they'll do space heating and they'll also do domestic hot water. And when I was talking with the folks from HPAC this year about the live build, I threw out the idea, since we're talking about air-to-water heat pumps, how about we build a board that incorporates an air-to-water heat pump and a boiler, similar to what we were talking about this morning. So I sent them up a schematic, and this is what I have to show you. I know it's pretty small, but I want to just talk a little bit about what this system is. It's a pretty simple heating-only system at this point. So it has an air-to-water heat pump, a monoblock. Now, we don't actually have a heat pump up here, but on the upper left corner of the board, you can see a couple pipes that go up. Those would be the pipes that go up eventually to the heat pump. So think of those pipes as going through an outside wall, and they'll connect to the monoblock heat pump. So that's starting over here on the left. And then once we get inside, we've got a piping circuit that goes over to a buffer tank, and you can see down at the bottom here a small buffer tank. And they're just completing the piping on that now. Over on the far right side of the buffer tank are 3 standard zone circuits that each have a circulator in there, and then you can see the returns over on the far right. So that's all pretty much standard fare. We've been doing that for years. What is new and different about this schematic is actually in this area right here. And the components that are in there are not exactly what you would have in a real system, but I'll explain what's going on. One of the characteristics that many heat pumps, air-to-water heat pumps, have in their internal controls, they will turn on the circulator 2 to 3 minutes before the compressor starts, okay? And they do that to verify that there's adequate flow and sustained flow, because, as you know, you don't want to start a compressor and a heat pump if you don't have fluid flow, either air or water, to bring heat in or take heat away. So we have that 2 to 3 minute period where the circulator is running, but there's no heat being produced. So here's the problem. Over here we've got a buffer tank, and again, this is a very small tank, so you wouldn't get a lot of temperature stratification in that tank, but temperature stratification in a buffer tank is desirable. We want to keep the hottest water at the top, the coolest water at the bottom. So you see the red at the top of this diagram and the blue at the bottom. We don't want to disturb that, okay? There are good thermodynamic arguments favoring stratified tanks. Now, what's going to happen if we turn on this circulator and we circulate fluid through the heat pump, the compressor's not running, and it goes back through the buffer tank? It's going to flip the tank temperature. Basically, it's going to pump water from the bottom of the tank through the heat pump, not change its temperature, and then pump it into the top of the tank. So we're basically destroying a desirable trait of that tank, the temperature stratification. Now, there are different ways to get around that, but one of the concepts that the overall piping is meant to show you is right here. You see this ball valve. That's actually supposed to be a motorized valve. And there's another valve right here, a zone valve, and this could work if it has a high enough flow rate, CV rating. But ideally, this would be a motorized ball valve, and this could be a zone valve. So how does it work? Well, when the heat pump first starts up, this valve would be closed. This valve would be open. So now we have a closed loop between here and the heat pump. This is where the flow is going to go when the pump in the heat pump, the circulator in the heat pump first turns on. So we're recirculating, and what we're doing is we're waiting for that fluid to come up to temperature. We don't want to pump 70-degree water into the top of a buffer tank that might be at, pick a number, 110 degrees. Once the temperature of the water leaving the heat pump has risen to, or maybe slightly above the temperature at the top of the buffer tank, we're going to close the bypass valve. And again, this is just mock-up. So this would be a motorized valve. This valve would close, this valve would open, and you could see the flow path going over to the buffer tank at that point. Now, I mentioned this is a heating-only system. If you're incorporating cooling, there's another reason you'd want to have that valve there. One of the things you don't want to do, imagine an air-to-water heat pump. In the summer, you could have a system that is doing both domestic hot water heating through, let's say, an indirect tank, or possibly even coils inside that buffer tank, and it could be doing cooling. So what happens if both loads call at the same time? We get a call for cooling, and we get a call for heating, or domestic water heating at the same time. Well, one of them's got to take priority. The heat pump can't operate as a heating device and a cooling device at the same time. So let's say that we could pick either one as the priority. Imagine we have got, let's see how we do it. Let's say cooling is the priority. The cooling load's been operating, so the piping between the buffer tank, this piping in here going out to the heat pump, it's got chilled fluid in it. That fluid could be 45, 50 degrees Fahrenheit, okay? If we immediately switch that to domestic water heating, what's going to happen to that chilled fluid inside that pipe? Where is it going to go when the circulator turns on? It's going to push it right back into the indirect tank or into the buffer tank. So we're pushing a slug of cold fluid into that tank. We don't want to do that. And then the opposite is true as well. If we've been heating domestic water with the heat pump, and if the piping between the monoblock heat pump and that buffer tank, if that has hot fluid in it, it could be 120, 130 degree fluid potentially. If we immediately send that fluid over to a coil in an air handler, okay? Let's imagine you've got a ducted system for delivering cool, dehumidified air to the house, and all of a sudden we send a slug of 125 degree water into that coil. You're going to get a burst of warm air coming out of the diffusers, and you're going to get a complaint. You know, the occupants have turned the system on for cooling, and for a couple minutes, they're going to be feeling warm air coming out. Now, that's going to cool down pretty quickly because there's not a lot of thermal mass between that heat pump and that buffer tank, but still, you don't want that. So, if this system incorporated cooling, there would actually be another valve here in parallel with this going to the cooling coil. That valve would only open once that fluid temperature has dropped down to some suitable temperature to supply the coil and the air handler, let's say 45 degrees Fahrenheit. So that's a way to switch a heat pump from a heating mode to a cooling mode and allow that heat pump to run its circulator for 2 to 3 minutes before the compressor turns on, but not take that detrimental effect of flipping the buffer tank stratification or sending a slug of heated fluid into the coil of the air handler. We're going to talk about that more this afternoon at 3:45. But other than that, and you can see the boiler, by the way, the boiler is piped in parallel. Just a couple things here. Here's the circulator for the boiler. This circulator, again, it's there for purposes of just putting a circulator on a board. In general, that circulator is a little small for a heat pump. And it's actually probably good to talk about this. A zone circulator is just not enough in terms of flow and head to, especially a 4-ton heat pump. You need about 10 to 12 gallons per minute, but look at the head requirements. And it varies from one product to another. You might need 20 or 25 feet ahead at, let's say, 12 gallons a minute. You're not going to get that from a small zone circulator. So the good news is the flange size of that and the flange size of a larger circulator that would have the flow and the head requirements necessary are the same. So those isolation flanges can be closed right here. that circulator can come out, and a circulator with a higher curve, higher flow, higher head could go in place of it. I was amazed how fast this was put together with press fittings. I'm old school. I learned how to solder pipe about 40 years ago. I can still solder pipe, but press tools are great. And I've watched the changeover, if you will, in the hydronics market over the last, 10 to 15 years. It's rare to see a hydronic system today that has soldered pipe in it, from my experience. So press fittings are really nice in that respect, and it got put together very quickly. Control-wise, you can see they've got a zone relay board over here. There's a zone relay board that can operate this. So again, just because it's a heat pump and a boiler, the zone circuits run the same way. They get a call from a thermostat, just turns on the associated circulator. The heat is going to be coming from the buffer tank, and it's basically up to the boiler and the heat pump to maintain the buffer tank temperature. Typically, we would use a two-stage controller there. First stage is going to operate the heat pump. If the heat pump can't keep up with the target temperature requirement in the buffer tank, then the second stage contacts would close. That would turn on the boiler, and the boiler circulator would turn on as well. So it could be a two-stage outdoor reset control. Since this is doing just space heating, outdoor reset, we talked about it this morning, the temperature in that tank could vary. As it gets warmer outside, we don't necessarily have to heat that buffer tank up to where we would be at design load conditions. The benefit of that, higher COP, higher capacity in the heat pump. It does get a little bit more complicated when you bring domestic water heating into the picture. If this tank was going to have internal coils for domestic water heating, we call that a reverse indirect. Okay, the domestic water would go through the internal coils, and the system fluid, which in this case, since it's a monoblock heat pump, it would be a mix of water and antifreeze. That's going to be in the shell of the tank, okay? If we do outdoor reset on the tank temperature, what's going to happen to our domestic hot water delivery temperature when it gets warmer outside? Let's say it's 40 degrees Fahrenheit outside. That buffer tank might only, depending on what the heat emitters are, the buffer tank might only be 90, 95 degrees. It's warm, but it's not warm enough to fully heat that domestic hot water. Now, what could you do? You could put another heater downstream of those coils. You could treat the buffer tank and the coils as the preheating device. That might bring the water from, and again, I apologize, I'm in degrees Fahrenheit. Let's say we bring the water from 50 to maybe 90 degrees through the coils in the tank. Then you could go into a conventional electric, gas, instantaneous, any other kind of water heater, and you're supplying that water heater with preheated water at 90 degrees. That's a major part of the temperature lift. So your heat pump can still contribute some heat to domestic water, even if you use outdoor reset on the tank. But my own preference would be to use a set point, two-stage set point control. Keep the buffer tank, depending on what your domestic water requirements are, probably keep the buffer tank from 115 to maybe 125. So the heat pump and the boiler would just maintain the tank between 115 and 125 degrees Fahrenheit. And if you're going out to panel radiators, fan coils, that's definitely warm enough for panel radiators when they're sized properly. If you're going out to radiant floor circuits, depending on what the circuits are, if they're tube and plate, you're probably going to be fine without a mixing system. If you're going out to a slab, you would have a mixing device between the buffer tank and your zone circuits, which again, we've done that for years. So I think one of the points I want to make, even though we are incorporating a heat pump in here, it's pretty much all available hardware. The controls that would operate these motorized valves, that would do the bypass and so forth, those could be as simple as a differential temperature controller that looks at the temperature at the top of the buffer tank and compares it to the temperature coming out from the heat pump. And once that heat pump outlet temperature is up to, or maybe a little bit above the buffer tank temperature, you enable that flow to go to the tank. So again, very basic heating only system, but as we're going to talk about this afternoon, when we bring cooling and domestic hot water into the system, the controls do get a little bit more sophisticated, but we have off-the-shelf controls now that can handle the majority of the functions that we need there. Any questions on the build itself? He builds them so fast, you know, he gets it done before it even comes in here, almost.
It's a team effort.
Yeah. You can see he's got a condensate neutralizer under the boiler there. You got the expansion tank in there. You aren't using PVC venting, which is good. Is PVC venting still allowed in Canada on ModCon boilers? I've never been a fan of it, but anyway, we have a panel that is functional, or will be functional with a couple small changes in those valves there, that can operate both from a heat pump as well as a boiler and do 3 zones. So, nice job. I appreciate you guys putting it together. Like the t-shirts too.
Thank you.
Any other questions? Okay. That's all I've got, folks.